Hey, welcome back to Physical Science. I'm glad you're here, okay? I hope you're safe and everybody in your family is safe and healthy. We got something new to do today. Last time we were together, what we talked about was how to find the number of protons, neutrons, and electrons so that we could use that to figure out what's going to go on as far as future reactions, chemical properties, all that kind of stuff. Well, what we're going to do today, well, going back to the last thing we did, we determined the number one rule of thumb was that if it's the proton, the number of protons is going to determine which element it is, okay? So if you have 3 protons, for example, that we went over last time, if you have 3 protons, there's only one element on the entire periodic table. Make sure you got your periodic table out. There's only one element that has 3 protons. Okay? If you go down to 2 protons, well, that's helium. It's no longer lithium. If you go up to 4 protons, well, that's beryllium. Okay? So, the number of protons determines which element it's going to be on the periodic table. Now, today, we're going to mess around with something. Today, we're going to mess around with one of the other 2 things, because that's our next couple lessons. If you change the number of protons, that gives you a different element. Well, what happens if you mess around with the number of neutrons, and what happens if you mess around with the number of electrons? That's the next 2 lessons, okay? So that's what we're going to do today. Now, in real life, if you go out there in nature and you do all these chemical tests and you find and you search for beryllium, you're going to find out that even though you did find beryllium, some of it's one color, some of it's another color. Some of it may be soft, some of it may be as hard as granite. You just can't figure it out, but they're all still beryllium, but they have different properties, okay? Well, it turns out in nature, when you look at this periodic table, which of course you got yours out, if you look at this periodic table, each element, excuse me, each element on here can have different kinds of that element. So in other words, beryllium can have different kinds of beryllium, okay? And that's what we're going to talk about today. How do you get different kinds of the same element, but still get different kinds, okay? So what we're going to do is we're going to do our P and E, but we're going to do it for 3 different kinds of beryllium, okay? 3 different kinds of beryllium. There's this one right here, this one right here, and this one right here. Now, the beryllium that's on your periodic table, it goes like this. It says this, 9.012, and there's a 4 up here. So you can see it looks a lot like these 3 that I gave to you, but there's a big difference. Look at that mass down there on the bottom. These are whole numbers. They're not some little 0.0 whatever, blah, 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 blah after the end of it. They're whole numbers. That means that each one of these berylliums have a different mass. Remember, this is the atomic number. The big number is the big mass, big atomic mass. So the big numbers down here are changing, okay? They're changing, and that's what creates the different kinds of beryllium, or different kinds of an element. So let's do our P and E and find out exactly what's going on. Now, let's see, remember, number of protons. Which one of these 2 numbers is the number of protons? Remember, it's always a small number, so it's the small one up here. So this is going to be 4 protons. Let's go to the next one. Beryllium, how many protons does it have? Of course, it's the same, 4, right? It's always a small number, 4. See, each one of these is beryllium, so you notice the number of protons never changes. Otherwise, it would change elements, right? So we still got 4 protons up here. Now let's do the next part. This was the tricky part we learned last time. How do you find the number of neutrons? Remember, you had to subtract 2 numbers. You take the big number and you subtract the small number from it. So we're going to take 7, and now notice we don't have to round anything anymore because we're going to give you a whole number from now on. So you got 7 minus 4. So this one's got 3 neutrons. And the number of electrons, excuse me, number of electrons, we're going to do the same. You got the same number, positive, negative, keep everything balanced, right? That's what nature likes, balance. So if you got 4 positive charges, you're going to want 4 negative charges. All right, let's do the next one. This beryllium right here, remember you take the big number, 10, subtract the small number, 4. This one's got 6 neutrons. Well, what about the electrons? The electrons, you got 4 positives, supposed to have 4 negatives. So that stays the same. That's not changing. Over here in this last one, again, to get the number of neutrons, you're going to take the big number minus the little number. So 11 minus 4 is 7. So this one's going to have 7 neutrons. And number of positive negatives got to stay the same. So this one's going to have 4 electrons. Now, you take a look at that. What is the one thing, the only thing that's changing that makes this kind of beryllium and this kind of beryllium and this kind of beryllium? What is it that's changing? It's the number of neutrons, right? Look at that. Right here you've got 3 neutrons, 6 neutrons, 7 neutrons. And this isn't all the different kinds of beryllium. There's even more. Carbon has 24 different kinds of different kinds of carbon out there. Okay? It's crazy. Now, while we got this up here, see, this one's got a mass of 7, this one's got a mass of 10, this one's got a mass of 11. Now, this is a good time for me to tell you why this number is so odd. Why has it got a decimal on it? It's because if you want to figure out what mass to put in there, what we do is we go out in nature, we find all the different kinds of beryllium that we can, we measure the mass of each one of them, we record it, and then we do what's called a weighted means, or basically taking an average. So if we take an average in nature using what's called weighted means, the average comes out to 9.012. It's not going to be a whole number, okay? So that's why this number is not a whole number on your periodic table. It's because it's the average of all the masses, okay? Maybe I should put that up here. This is the average of all the masses, okay? It's the average of all the different kinds of masses of beryllium. Okay? Now, this now has a special name. Okay? When you change the number of neutrons in an element, what it does is it creates something new. These different kinds of beryllium are called isotopes. Okay? This is one of those words you want to put over in the margin. Make sure you remember the vocabulary like we talked about before. These are called isotopes. Okay? Those are called isotopes. So we would say that these 3 berylliums, these are 3 different kinds of isotopes of beryllium. That's what we would say. There are 3 different kinds of isotopes of beryllium. So we could actually write that on there so you can get used to hearing the phrase. These are isotopes of beryllium. Okay? These are isotopes of beryllium. Now, where have you heard the term isotopes before? Well, last time I heard it, it was at the hospital, right? Somebody had to get a CAT scan done. So they take the syringe and then they inject some stuff into you. And then for some reason it shows up on the x-ray, on the CAT scan. Well, those are called radioactive isotopes. Okay? Those are isotopes of different kinds of elements. And those particular isotopes are just slightly radioactive. Not bad radioactive, like cause cancer radioactive. We're talking something that gives off something called an alpha wave or an alpha particle. Now what happens is they squirt that in your body, it begins to emit these little tiny alpha particles out, and then that great big x-ray machine above and below you, they record those little alpha particles coming out. And those little particles come out in the exact shape of whatever they're trying to take a picture of. Right? If they want to take a look at your gallbladder, they'll inject it over there, and then your gallbladder starts emitting these little alpha particles, and it gives them a beautiful 3D picture of your gallbladder to make sure it's still working or if it needs to get taken out. Okay? So we use isotopes for all kinds of things. They're not all radioactive, okay? But there are many, 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 many different kinds of isotopes. So 2 rules of thumb. Number 1, make sure you got this written down. I'm going to make sure you know this. Don't ever forget it. Number 1. Protons determines the element, right? Isotopes create, neutrons, sorry about that. Neutrons create isotopes. Protons determines the element, Neutrons create the isotopes. Okay, so there's two rules of thumb. Protons, elements, neutrons, isotopes. Make sure you got those stuck in your head up there, okay? So make sure you write those down. Now, last thing I'm going to go over with you real quick, well, second to the last thing I want to do, is I want to show you how they're going to show you these. If they ask you to do the PNE for some particular isotope of beryllium, they're not going to show it to you like this. They're not going to say BE 11 and a 4. Okay, there's other ways to show it. One of the ways they like to do this in chemistry books is they'll show you, like, let's say this BE right here. They would write down BE, and then they put on a great big hyphen, a great big dash. It's not a negative sign, it's just a big dash. And then they put the mass afterward, because that's what's important, right? That mass is changing because the number of neutrons is changing. Not the number of protons, just the number of neutrons. So they put the mass on there, okay? So this one would be BE, big dash, and what's the mass? It's the big number. Remember, the big number is the mass. That would be BE 10. And this one would be BE 11. So if you ever see an element expressed like that, that's very special. That's not just some average of all the isotopes of beryllium out there. No. They want you to calculate the exact proton, neutron, electron for this one isotope of beryllium 7. This would be beryllium 10. This would be beryllium 11. Okay? Now, you've heard of other things like this before. How do you determine how old the bones are of a dinosaur? Okay? What do? Look at the date that it was stamped, it was made? No, right? That doesn't exist. You do something called carbon dating, right? You use something called carbon dating. And in carbon dating, they are checking for carbon 14. That's a special isotope of carbon. And they can tell based on carbon 14, how much is in your body or in the dinosaur bone, will tell them how old it is, okay? There's also a carbon 12 that you can do dating on, okay? But each one of those is different, so you can try and figure out what the dates are and what have you. Now, let's go over a couple of examples, and then we'll be done, okay? What I'm going to do is I'm going to show you the different ways that they could show you an isotope, and you'll always be able to figure out the number of protons, the number of electrons, and the number of neutrons, okay? No matter what kind of crazy stuff they throw at you, you'll be able to figure it out. All right, so first we'll do this one. Let's do nitrogen 17. Let's try that one. Nitrogen 17. Now you look at that and you tell me, what's the number of protons, neutrons, and the electrons? Well, I look at this thing and it says nitrogen 17. Now, how many protons does nitrogen 17 have? It's not 17, right? Because remember, that's the mass, right? So how am I going to find out what the atomic number or the number of protons nitrogen has? You got to go back to your periodic table, okay? So look at that periodic table you got. I know you brought it up, right? Because you're coming along with me here. And we're looking at that, and it says nitrogen. In your periodic table, it should show you nitrogen 7, and there's 1401 down here, okay? But they want you to look at just the isotope of nitrogen 17, not the average of all the ones out there in nature, just nitrogen 17. So, what we are going to need, though, is that right there. That tells us the number of protons and neutrons. So the only way, if they give this to you like this, the only way to find the number of protons is you got to go look at the periodic table. So we look at the periodic table and it says 7. How do you find the number of neutrons? You have to subtract the big number from the little number. Now here's the confusing part. Do I use this big number or do I use this big number? Which one do I use? You use the one they gave you. Okay? If they give you the number, use the number. That's the good rule of thumb. So this is the mass they want me to use. So I'm going to put a 17 right there. Subtract the number of protons, which is 7. That leaves me with 10 neutrons. Did you see that? And then, of course, same number of positives and negatives. So we're going to want the same number of positives and negatives. There's both 7. Cool? All right. Let me show you another one. Because now that you can see this, there's another way to express an isotope to somebody, okay? This is another way that they like to do it. Let's take a look at, phosphorus. Phosphorus. Excuse me. So phosphorus is a capital P, and sometimes they will give you the two numbers, okay? But instead of showing them up here and down here, what they may do is actually flip-flop them around. Okay, it all depends on which chemistry book you open up. So we're just going to get good at all of them. So that way you never get tricked. So let's say we got phosphorus. And let's say we got a 15 up here. And let's say the mass of this one is 35. Okay? Now, if you ever see that and the numbers are small and off to the side, it's just like if it was on the periodic table. But because they didn't give you some weird 0.0546 whatever number, they gave you an exact number on the mass. That means this is a special isotope of phosphorus. And not just any old phosphorus, this is an isotope, okay? So let's do this. We want to be able to do the proton, neutron, and electron. Number of protons. Remember, the number of protons is always the smaller number, okay? It's always a smaller number, no matter where it's at. They can put the 15 anywhere they want. Doesn't make any difference. The small number is always the number of protons. So the proton is 15 right here. Now we've got to find the number of neutrons. Remember, we got to subtract. They gave me this mass, so I'm going to use that mass. So we're going to use 35 minus the number of protons. This one's got 20 neutrons. And we're going to have the same number of positives and negatives. So the number of electrons is 15. You okay with that? All right. Now let me show you what happens, because every once in a while they will flip these two around. All depends on which book you open. It's crazy. But you're not going to have any problems with it, are you? Because you know, doesn't matter where you stick it. I know the small number is always the number of protons. The big number is always the big mass number, right? So let's try another one here, and I think we'll be done. Let's try iodine. Nah, that's too crazy. Let's try potassium. Potassium's got a lot of isotopes on it. So let's say we have potassium, but they give it to you switched around. So potassium, let's say they put the small number down here. Is that going to bother you? No, of course not. And let's say the mass that they want you to use is 40. Okay? If you look at your periodic table, the mass of potassium is 39.10. But remember, we're not going to use that mass because they gave me that mass, so I'm going to use that mass. Okay? So it's not going to be a problem. All right? So here we go. We're going to do our proton, neutron, electron. How many protons does potassium have? Remember, it's always the smaller number, right? It's not always the number on the top, it's always the smaller number. So this is the number 19 right here. How do you find the number of neutrons? You subtract, right? Take the big number, just like we've been doing, minus the small number. So 40 minus 19. Let's see, if that was 20, this would be 20. So it's one less, so we'll have one extra on there. So 21. So you got 21 neutrons, and the number of electrons, again, is still same number of positive negatives. We're going to keep it balanced until next time we meet. We're going to mess around with that later. But we'll have 19 there, and we'll still have 19 negatives there. Okay? These are the 3 ways that they could show you, or you will see, an isotope of an element in a chemistry book. So when you go on to college, okay, or if you get to work at a hospital and you're the radiologist making 6 figures, you know, and you got to figure out what to inject into somebody, you'll be able to read the numbers real good. You'll know it doesn't matter whether they show you the isotope this way, or this way. You got it covered. You can figure out the number of proton, neutron, electron, and do some other calculations that you have to do. Okay? All right. It has been great. I'm glad you've been here today. And once again, please make sure that you stay safe and you keep your family safe. I'll talk to you later. God bless you.